That was
$10 for a tip.
If you guys carry $40, yes.
I'm not paying for 40% or whatever percent. I'm only going to pay.
Okay, we're going to continue talking about simple harmonic motion.
Those are good.
Also, when we get our pulleys.
Yeah, it's supposed to be every time 20.
My pulley, and I need it now.
That's like 40.
Otherwise, he'll tip like $20 every single month. He's like, my grandpa, he's like, I know.
Okay, go ahead.
I was there one time.
What's wrong with your machine?
What machine?
What, I don't want what is the actual term? For the swinging
cradle. Somebody broke it again.
Seriously?
And then a student got me new ones, and they're just not good.
Hey, wasn't it shiny?
New balls?
Actually, that's probably the best I've ever seen it do. Normally,
Yeah, I think we're shiny. You broke your old ones.
Yeah, that was hilarious too.
Yeah.
I know. Most kids who ruin my stuff don't mean to.
I do. You ruin most of your stuff, to be fair.
Busted your butt.
Okay, that's not one.
Okay.
Boy.
I'm not bitter about that.
Emma, stop it.
I'd rather you just completely ignored me. There's a few of you that did that. Simple harmonic motion describes any periodic motion that is the result of a restoring force that is proportional to displacement. This is kind of your little definition of what you need to have simple harmonic motion. Okay, because of the restoring motion, or restoring force, what you tend to have during simple harmonic motion is a repeated motion. A back and forth motion. That makes sense?
Yes.
Okay? Which is what?
I'm sorry, I'm tall.
You're tall, but you don't have to like sprawl out.
Wait, can I scroll? Hey, don't scroll.
Alright, this is where it gets fun.
So good and tasty.
So, a simple pendulum consists of a mass called a bob. Have you heard that?
Bits and bobs.
It's a so anything that's tied to the end of a string or something along the lines of that, you would call a bob. So technically, what is that playground game with the ball?
Tetherball?
Yeah, that's technically a bob. The ball
So
is
you're just smacking that ball.
You're smacking the ball.
There you go.
Oh yeah, it's like a fishing, or like a bob.
That's a bobber.
A bobber? Right?
Yeah, I mean, that's the top of the bob. Okay, so here we go. If we look here, you can imagine that you would have your tension force due to the what?
Gravity.
What would cause the tension force? The string.
Oh,
Tension. Right? Okay. And then also you would have a gravitational force, and we're going to assume air resistance because we know that there would also be air resistance force going on here. But technically, when you're swinging a bob, all you really have is a tension force and a gravitational force, right? Okay? And gravity always points directly where?
Down.
Down. Okay? So if you think about this, if gravity points directly down, then would you ever have gravity completely removing the tension force? Like equal and opposite, ever? At one point, yes. What is that one point?
Resting.
Resting, or when it's at its straight down position, right? And we talked about when you're at equilibrium, your force is
Zero.
0, right? So if I just have a bob, you would say that the tension force and the gravity force are going to completely balance each other out, where you have a net force of 0 only at that one spot. And we talked about yesterday how when you're at equilibrium, or you haven't gone away from where your equilibrium position is, you have a net force always of 0. Therefore, you have an acceleration of 0. But if you're moving, this is where you're moving the
Maximum.
unless you're at rest. Okay? Now, if you look, I can break this gravitational vector up into an x and y component. Yeah? Yeah. Okay, so your y component here will almost perfectly cancel out the tension force. Why do I say almost perfectly?
It's not quite. It's not going perfect other than Jesus.
Yeah, but okay. So the reason why it's not going to is you would have to have all of the gravitational force to cancel out with the tension force, right? And if some of it is in the x direction, then you're not going to have the full sum in the y direction, will you?
Well, isn't it technically like all of the vectors?
It's not straight up and down.
Gravity's up and down, but the other thing is.
So you're changing your x, y plane. Okay, so now, this should make sense. When you're swinging, usually there's some downward movement, isn't there? Right?
Yeah.
When you swing,
Yes.
there's a downward movement, right? And that makes sense why this isn't going to be, right? This is, the lowest point is here, so it's going to move down what, that much. It is a little bit weird, but you can take any vector, break it up into an x and y component, it's possible. No, gravity's straight down, everything else is
X
sideways.
component is sideways.
Yeah, we're saying that our x-axis is that.
That is
Did you
Okay.
draw this thing too?
Yeah.
I was checking it.
All right, now, any displacement from equilibrium, or the weight of the bob, would be your Fg, can be resolved into your two components. Your x component of your weight is what we would call our what?
Restoring.
There's thing that gets it back to 0 slot.
So if I'm to the right of equilibrium, my restoring force will be left. If I'm to the left of equilibrium, my restoring force will be right.
Tell me it's
How can we be to the side of equilibrium?
They're not. Equilibrium straight up and down in this context. So to the right. I mean, the one where we use the spring mass system, that wasn't up and down, but you could still say to the right or to the left.
So
of
you're
equilibrium.
saying you'll move to the right and then to restore back to equilibrium, then move back to the left.
And the force, even if I'm here and I'm swinging this way, as I'm swinging this way, my restoring force is still that way. It's just slowing it down.
Because that's the way you want to go back.
Yeah. And then when I'm going back, now I'm speeding up with the restoring force. Okay? Now, this is kind of goofy, but we in physics like to make everything not realistic. So,
Jacob's spice of life.
no, don't do that, dude. The magnitude of the restoring force is going to be, that's a G. I don't know if does it come up as G on your do you even have it on
No,
your?
it's FQ.
Yeah, it's F.
What?
Is it G? Okay. Ouch. So, how we find the restoring force is simply taking the weight sine of theta, because sine gives you your x component if you remember Pt2, which I hope you do. I assume you
I just theta looks like
It is a mess up.
Theta is fine on this.
do. Wow, so I'm this is more advanced.
Yeah, we're quite
Basically,
Take anything.
Now, it says that when the maximum angle of displacement is relatively small. Okay, so what this is simply saying is, in order for simple harmonic motion to be the case in these pendulum motion problems, you need to have it only swing out to a maximum of 15 degrees. That is the only situation where the displacement is proportional to the restoring force. When you get above 15 degrees, it must have to do with the fact that the angle is getting so big that the displacement is no longer proportional to the restoring force. And so therefore you cannot call it simple harmonic motion. Is it still back and forth motion? Yes, but yes. Okay? So, as a result, the restoring force is going to be nearly proportional to displacement when you've got it at 15 degrees or less. Anything above it, it's too much of an assumption to be okay. If that makes sense.
Do we need to write down
Like in your note card? You certainly can. But if you understand it conceptually, then I don't think you would need to.
Full face, full face.
Do I want to do this?
when you don't get the physics
Stop staring at me like that.
Well, I know
Somebody
Cameron
did
says
just-
no group of
I'm
three.
just hoping that it's fast.
This fails.
I failed?
Probably no.
What did I fail?
Yes.
Wait, are you wishing bad luck on me too then?
Did I push
Only
it?
has 8.
Laura, you were talking about Steven, right?
Oh, we have flashes.
So you're wishing bad luck on I thought you were talking just about Steven.
Okay, maybe. Alright, well, we'll show this anyways.
A simple pendulum consists of a mass called the bob
The bob.
hanging from a string. The restoring force in a simple pendulum is due to the force of gravity. If the bob is moved slightly to one side, we can examine that restoring force using a free body diagram. Tension acts on the bob through the string. The force of gravity can be broken into two components. One component exactly opposes the tension. The other is perpendicular to that. This
It's not
component is the
completely
restoring
true,
force.
but yeah.
When the displacement of the pendulum is very small, its motion approximates a straight line. In addition, for small angles, the restoring force is proportional to the displacement, and the motion of the pendulum is simple harmonic motion.
So what they're saying is, so what they said in that when they said that the Y component completely neutralizes the tension, that's not true, right?
Because we need the exit out.
Then you would never move up or down, right? Which we know there's a slight movement up and down as this swings back and forth. Okay? And so what it's saying is if you keep it in 15 degrees or less, it's pretty much like the bob is just going like this. And there's no that. So you could say that the restoring force is perfectly, almost perfectly proportional to its displacement away from equilibrium. Okay? Now, this is something that you're going to want to, I don't know, is this in your notes?
Yeah.
This is an important slide, an important thing that you might want to, I don't know, star, just because it takes what we've talked about and puts it in two separate pictures and helps us understand the relationship between your force, your acceleration, and whether you're at your maximum speed or your minimum speed. So this is basically a visual version of what we had just from the notes. Does that make sense? Where we talked about, okay, what's happening at equilibrium, what's happening at max displacement. Okay? So you kind of see that here are the two situations. We talked about this yesterday, we're talking about this today. Here we're saying we're at our max displacement. So if we're at our max displacement, what's true about the velocity?
0.
Should be 0, right? Because it's right before it stopped to come back, right? Okay? But it also is going to have our maximum force because we're the most stretched or we have the biggest restoring force at that point. Okay? And so maximum force is going to give us a maximum what? Acceleration. Make sense? Okay? Then it restores back to equilibrium. We can talk about our equilibrium position. Our gravity now completely outweighs our tension force, so we should have 0 force at that point, or a net force of 0, which means our acceleration then has to be 0. And the reason why we're at a maximum speed is because we were speeding up to get to that point. Make sense? And then it just continues both directions.
Wait, Kramer, what are the arrows?
What direction it's going?
What is that?
So like this is saying yeah, so like the force here. So like that's a stretch force, so it's pulling that way, right? Does that make sense? Like if I stretch a spring, in this context of this picture, this visual here, is the spring pulling this way or is it going that way? Which force would it be?
I'm confused, like, which way is the spring going?
Not asking you which way the spring is being stretched, which way is the spring applying a force?
Oh, okay.
Does that make sense? So you would say that way. Okay, so because the force is that way, you would also say the acceleration is that way, even though technically we're at no movement at that point. Okay? It would make sense that we would accelerate that way because that's where we're going next. Okay? And the reason why you see velocity going that way is because it's swinging this way. So it's showing you the direction of each of these things in this particular visual. Okay? Any questions? So this visually represents what we talked about yesterday. We're visually done.
Yeah.
Wow! That's good.
Wow, what productive physics class.
This is the most productive physics class we've ever had.
This was a short lesson.
It was a little short lesson.
I'm so
What's the difference
I'm gonna
between
get-
the first one and the last one?
Alright, quick game of playing.
So it's here.
There we go.
There's the merit.
What's this?